According to the National Electrical Code Section 450.3 ATWO, a primary overcurrent protective device, or OCPT, is generally required for transformers operating at over 600 volts. This requirement is in place to protect the transformer from overloads and short circuits, ensuring the safety and reliability of the electrical system. The code mandates this protection to prevent damage to the transformer itself, as well as to minimize the risk of fire or other hazards that could arise from electrical faults. There are exceptions to this rule, which are detailed in subsequent sections of the code. However, it is important to understand the general requirement first before considering any exceptions. One common scenario where the question of overcurrent protection arises is when tapping a transformer primary to a power source, such as a generator bus. In these situations, the length of the tap conductors is a critical factor in determining whether an overcurrent protective device is required at the primary connection point. The National Electrical Code provides specific guidelines for tap conductors, outlining the conditions under which they are permitted without additional overcurrent protection. One exception to the general rule requiring a primary overcurrent protective device is found in NEC section 450.3 FR. This exception, often referred to as the tap rule, allows for the primary conductors of a transformer to be tapped to a supply without overcurrent protection at the tap point, provided certain conditions are met. These conditions typically involve the length of the tap conductors, their ampacity, and the overcurrent protection provided at the supply end of the tap. However, it's crucial to understand the specific limitations and requirements of this exception, as it does not apply universally to all transformer installations. It's important to note that the exception in NEC section 450.3 FR does not apply to a transformer primary connected to a generator. This is because generators are considered a unique power source with their own specific protection requirements. The code recognizes that generators have different characteristics than utility power sources, and therefore, different rules apply. When a transformer is connected to a generator, the generator's overcurrent protection is generally not considered sufficient to protect the transformer itself. Therefore, a separate overcurrent protective device is typically required at the transformer primary, regardless of the tap length. The rationale behind this requirement is that generators can have varying fault current capabilities, and their overcurrent protection may not always coordinate effectively with the transformer's thermal withstand characteristics. In other words, the generator's breaker might not trip quickly enough to prevent damage to the transformer in the event of a fault. Furthermore, generators are often used in emergency or backup power systems where reliability is paramount. The code aims to ensure that a fault in the transformer does not cause the entire generator system to shut down, which could have critical consequences in certain applications. Therefore, a separate overcurrent protective device at the transformer primary provides an additional layer of protection, enhancing the overall reliability of the system. The key takeaway is that when dealing with transformers connected to generators, the standard tap rules for transformer primary conductors do not apply. Instead, the transformer must have its own dedicated overcurrent protection, sized and installed in accordance with the National Electrical Code. This requirement is in place to protect the transformer from overloads and short circuits, as well as to ensure the safety and reliability of the generator system. When designing and installing transformer systems connected to generators, it is essential to carefully review the relevant sections of the National Electrical Code and consult with a qualified electrical engineer. This will help ensure that the installation meets all applicable code requirements and that the system is properly protected against electrical faults. It's also important to consider the specific characteristics of the generator being used, including its fault current capabilities and its overcurrent protection settings. These factors can influence the selection and sizing of the transformer's overcurrent protective device. In addition to the National Electrical Code, local codes and regulations may also apply to transformer installations. It is important to check with the local electrical authority to determine if there are any additional requirements that must be met. By following these guidelines and consulting with qualified professionals, you can ensure that your transformer system is installed safely and reliably, and that it meets all applicable code requirements. Remember, electrical safety is paramount, and it is always best to err on the side of caution when dealing with electrical systems. In summary, a transformer with a primary voltage of 13,800 volts stepping down to 300 volts that is connected to a 13,800 volt generator bus requires a primary overcurrent protected device, or OCT, as per NEC section 450.3 ATWO. The exception in NEC section 450.3 FR, which allows for taps without primary OCT under certain conditions, does not apply when the transformer is connected to a generator. This is regardless of the tap length, even if it is within 8 feet. The reason for this is that generators are considered a unique power source with specific protection requirements that differ from utility power sources. Therefore, to ensure the safety and reliability of the electrical system, a separate overcurrent protective device is required at the transformer primary. This device must be sized and installed in accordance with the National Electrical Code and any applicable local codes or regulations. Consulting with a qualified electrical engineer is recommended to ensure that the installation meets all requirements and provides adequate protection for the transformer and the generator system. Furthermore, it is important to understand the coordination between the generator's overcurrent protection and the transformer's thermal withstand characteristics. The generator's breaker should trip quickly enough to prevent damage to the transformer in the event of a fault. If the generator's overcurrent protection is not sufficient, a separate overcurrent protective device at the transformer primary is essential to provide an additional layer of protection. This helps to prevent damage to the transformer, minimize the risk of fire or other hazards, and enhance the overall reliability of the system. In addition to overcurrent protection, other safety measures should also be considered for transformer installations, such as proper grounding, surge protection, and regular maintenance. These measures can help to prevent electrical faults, protect equipment from damage, and ensure the safety of personnel working on or near the system. It is also important to train personnel on the proper operation and maintenance of transformer systems, including emergency procedures in case of electrical faults or other hazards. Regular inspections and testing should be performed to identify any potential problems before they become serious. By implementing a comprehensive safety program, you can minimize the risk of electrical accidents and ensure the long-term reliability of your transformer system. Remember, electrical safety is a shared responsibility, and everyone should be aware of the potential hazards associated with electrical systems and take steps to prevent accidents. This includes following all applicable codes and regulations, using appropriate personal protective equipment, and seeking assistance from qualified professionals when needed. By working together, we can create a safer and more reliable electrical environment for everyone. The primary function of an overcurrent protective device, whether it is a fuse or a circuit breaker, is to interrupt the flow of current when it exceeds a predetermined safe level. This level is typically based on the ampacity of the conductors or the rating of the equipment being protected. When an overcurrent occurs, the protective device will trip or blow, interrupting the circuit and preventing further damage. There are two main types of overcurrents: overloads and short circuits. An overload is an excessive current that flows through a circuit due to an increased demand for power. Overloads can be caused by things like too many appliances being plugged into a circuit, or a motor drawing more current than it is rated for. Short circuits, on the other hand, are caused by a direct connection between two conductors that have different potentials. This can happen when insulation on a wire is damaged, or when a conductive object comes into contact with two energized conductors. Short circuits can cause very high currents to flow, which can quickly damage equipment and cause fires. Overcurrent protective devices are designed to protect against both overloads and short circuits. They are typically sized to trip or blow at a current level that is slightly above the normal operating current of the circuit. This allows for temporary overloads, such as when a motor starts up, without tripping the protective device. However, if the overcurrent persists for too long, or if it is caused by a short circuit, the protective device will trip quickly to prevent damage. The selection of the appropriate overcurrent protective device for a particular application depends on a number of factors, including the ampacity of the conductors, the rating of the equipment being protected, and the type of load being served. It is important to consult with a qualified electrical engineer or electrician to ensure that the correct protective device is selected and installed. In addition to overcurrent protection, transformers may also require other types of protection such as voltage protection and temperature protection. Voltage protection is used to protect the transformer from overvoltages which can be caused by things like lightning strikes or switching surges. Temperature protection is used to protect the transformer from overheating, which can be caused by overloads or short circuits. The specific protection requirements for a transformer will depend on its size, voltage, and application. It is important to consult with a qualified electrical engineer or electrician to determine the appropriate protection measures for your transformer. The NEC, or National Electrical Code, provides comprehensive guidelines for the safe installation and operation of electrical systems, including transformers. It is essential to adhere to the NEC requirements to ensure the safety and reliability of your electrical system. The NEC is updated every 3 years to reflect changes in technology and industry best practices. It is important to stay up to date in the latest NEC requirements to ensure that your electrical system is in compliance. The NEC is not a law itself, but it is often adopted by state and local governments as the basis for their electrical codes. This means that compliance with the NEC is legally required in many jurisdictions. Failure to comply with the NEC can result in fines, penalties, and even legal action. In addition to the NEC, there may be other applicable codes and standards that apply to your transformer installation. It is important to check with your local electrical authority to determine what requirements apply in your area. By following the NEC and other applicable codes and standards, you can ensure that your transformer system is installed safely and reliably. This will help to protect your equipment, your personnel, and the public from electrical hazards.